The speaker now is Dimitri Coelho-Molo from Umar University, and he talks about the understanding. You change the title.
Yeah, no, it's large language models.
Okay.
It's just the abbreviation.
From benchmarks to functional ontology. The floor is yours.
Yeah, so thanks. And apologies, everyone. Is the volume of my voice okay? Because I'm still I'm having a severe case of airplane ear. So it feels for a week or so, it feels like I'm underwater. So I have very difficult time understanding exactly how loud I'm speaking or not speaking. All right, so what I'm going to be talking about today is something that is, so to speak, in the area that we might call the philosophy of science of AI, and more specifically of deep learning. So what I'm going to be talking about is questions about understanding and explanation of deep learning systems. So pretty much all the systems that you hear about nowadays when it comes to AI. I'm going to use some insights coming from cognitive science to suggest that one promising way to go about and increase our understanding of these very complex and large systems is by employing some lessons from cognitive ontology, or the whole debate on cognitive ontology that has exercised philosophers and neuroscientists for the past almost 20 years, since the inaugural Price and Friston paper from 2005, if I recall correctly. And then I'm going to provide an illustration for how this approach could work based on benchmark task that I designed together with other philosophers that is now part of this very large benchmark that was sort of promoted by Google called Big Bench, or Beyond the Imitation Game benchmark. All right, so the first thing to discuss is the fact that lots of these large language models, or LLMs, as well as other large pre-trained AI systems or neural networks, which sometimes are called foundational models or foundation models, they are most often evaluated by means of appeal to benchmarks, such as the Beyond the Imitation Game benchmark by Google. And this is a very, very popular, if not the, by far the most used method of evaluating these neural networks. And indeed, we have seen in the past years proliferation of such benchmarks, pretty much together with the new wave of AI research that came since 2012, and this kind of third wave of connectionism that we are living through. We have seen that developments in AI have come together with these new benchmarks that keep being produced to try and assess the capabilities of these systems. So we have here some examples. So Wino Grande, Truthful Q&A, and so on and so forth. And these systems, or these methods are used at least in two different ways. So one first way of using them is in more practical terms. So let's say you want to know what your neural network is good enough for, it is reliable enough for when it comes to practical applications. So you can use these benchmarks, and tailor or choose the benchmarks depending on which kinds of applications you are interested in, and then you study the reliability of your planned AI application by appeal to these to results in these benchmarks. Another use of this method is more theoretical, if you wish, namely that of studying the capacities of AI systems themselves, so what they can and cannot do, over and beyond any issue about or any question about their practical usability or reliability in specific situations or application cases. And that's what's going to be of most interest to me here, the second sort of use of benchmarks. Now, benchmarks are important and useful, and they have been throughout the history of AI, and especially for the past 11 years or so. But of course, they have some important limitations. So first, they are measures purely of performance. So they give us very little, if any, insights of what's going on under the hood, so to speak, in these systems. And often it is unclear what the benchmarks really probe, right? So we may start from sort of inferences in terms of, well, what would a human need to do in order to solve this task? And then we extrapolate from that to say, well, if humans need these and these capacities to be able to succeed in this task, then if a neural network also succeeds, then it is likely using those same capacities. So it does possess those same capacities. So, but this is, of course, very tricky kind of inference for reasons that I'm going to explore more later on in this talk. And another limitation of benchmarks that has been found is that you may have a neural network that is very good on a specific benchmark, and you think, well, this benchmark is close enough to this other task that I'm interested in. So if it does well in this benchmark, in this test, then it's also going to do well in this other one. And that's not actually the case, right? We have cases in which even what to us would seem like similar tasks that for which success on one of them would allow us to think, well, there's going to be success also in this other one, don't actually succeed, don't actually work in that way. Now, another strategy that can be used and has been gathering growing interest in the past few years is what has come to be called mechanistic interpretability. So people like Chris Olah, for example, from Anthropic, has invested a lot on this kind of research approach. So this is growing, and the idea here is to focus not only or not mostly on performance measures, such as benchmarks, but rather on trying to figure out the mechanistic functioning of specific kinds of AI architectures. So Chris Olah and his lab have all this work about, the mechanistic workings of transformer architectures, right, that are behind large language models, and not only nowadays. So they may ask questions like, well, what are the mechanisms that allow, say, large language models to do variable binding or to do semantic composition, or how can convolutional neural networks implement something like position-independent feature detectors, right? And then we can give, or they try to produce mechanistic stories about, well, what is it that is going on there in, a certain layer, such that we get, say, a hierarchical organization of, these position-independent feature detectors from simpler to more complex sorts of features, for example, as we see in CNNs. So there's quite some work on this and growing interest. And it's a particularly useful approach if you're interested in, really looking under the hood and trying to understand how do these systems manage to solve or to, successfully solve or answer questions or solve certain tasks and so on and so forth, and their limitations as well, right? So we may also be able to bring some more clarity on for what regards what they cannot do or what they may not be reliable in doing. But there are also some important limitations with mechanistic interpretability. So one very important limitation is that given the complexity of most neural networks nowadays, these techniques are only applicable to toy models. So even the work on transformers that I mentioned by Ola and his lab has only been used on very small transformer networks. It's just because it becomes intractable to do it with, any network that might be actually useful, right? And then you have to extrapolate from what you get from these very, very simplified toy networks that you can, apply these methods to, the ones that we actually use, which is of course a leap that is not so, straightforward to justify, especially when it comes, to these sorts of systems for which we have seen that size makes a big difference in workings and capabilities. And so we have very limited generalization powers with this, especially because, different sorts of networks that were trained in somewhat different ways that may have some variation in the stack of layers they have and vary in their size and so on and so forth, might not be captured to, a sufficient extent by this work on toy models. So we are sort in a difficult position, right? Because on one side we have these behavioral measures with all their limitations, which we also see, it's not, a new sort of limitation that comes from these pre-trained these large pre-trained models, but we also see when we are talking about human psychology, right? So there are limitations to what we can do with purely behavioral measures. And on the other side, if we want to look under the hood, we have this problem of intractability of anything that is, realistic and not, pure toy models. So we have benchmarks investigating performance, while mechanistic interpretability looks at the computational building blocks, if you wish, of these networks. But then there is the issue, right? So even putting to one side the fact that those computational building blocks that mechanistic interpretability help us perhaps review are, limited in the extent to which they actually capture how the large models work, we still need a source of connecting tissue between performance and the mechanism, right? So such that we can both look under the hoods and preserve some sort of generalization power, right? So that if we can say things about, I don't know, transformers in general and what they can achieve or not achieve. So what I'm going to explore here, the idea I'm going to explore is that cognitive science and the recent history of cognitive science can furnish us some useful cues or tips on how to proceed on this regard. And here I'm mostly referring to, as I mentioned at the beginning, to the whole debate on cognitive ontology. So here we have a nice diagram by Franken and Slors. It's already a somewhat old paper, but when we talk about concepts in cognitive science that we apply when we are trying to understand cognition, we can see that we actually use several different concepts, right? So we have a common sense concept that is used in everyday talk, such as memory or control, even though control is maybe not so common sense, but we can talk about visual perception and things like that. But that's of course a concept that is too messy, too tied with everyday usage, and is not particularly adequate for scientific work. And then we try to so to speak purify these common sense concepts and build scientific cognitive concepts that have the relationships to those everyday concepts. And that's not to say that that's what is usually done or even often done, but what hopefully should be done, right? When we try to talk about cognitive constructs in ways that are, scientifically adequate. So this also leads us to further refine those concepts. So we may find out that, or may theorize that memory should be subdivided into other concepts such as long-term memory, working memory, and so on and so forth. And then when we have this conceptual apparatus, and or in the process of building such a conceptual apparatus, we as cognitive scientists are also interested in finding ways to measure the presence and the use of those constructs in specific cases. And so we have to find a mapping or establish mappings between specific tasks and those constructs, right? So tasks such as here in the examples, like the Wisconsin card sorting task, right, which becomes a way to probe things like task switching or working memory capabilities, right? So we map that task, or we identify that task as a task that is adequate for probing that specific cognitive construct that we are interested in that specific case. And then, of course, there is the further task of trying to map those cognitive constructs onto neural structures or patterns of activation, anatomical areas, and things like that, right? So we may map some memory functions to hippocampus and things like that. Now, this is very typical in cognitive and comparative psychology. The extent to which we actually succeed in, avoiding all the baggage that comes with everyday concepts like, memory and perception, control and reasoning and so on. So the extent to which we succeed in going beyond the common sense concepts and having more carefully defined or characterized cognitive concepts is tricky. So I think there is lots of work still to be done there. But what we kind of see is that there is this bridge built by these cognitive constructs between the task performance and the neural implementation, right? So we talk about cognitive functions and cognitive capabilities as a source of in-between explanatory tool, right, between the nitty-gritty details of the neural implementation, or even if you wish, the computational implementation, and the performance in a certain task. Now, the question that cognitive ontology, as it has developed in the past years, asks is, well, fine, but what are the right categories, right? For each of those, so which are the right task categories, which are the right functional categories, and what are the right implementational categories, right? So which concepts should we be using for all these specific domains? Interestingly, as it started in 2005 and for quite a few years after, this took mostly the shape of a debate about how to map function to structure. So how to map cognitive constructs onto brain structures, right? So brain areas and stuff like that. But it soon became more than that, and it evolved into broader questions about what are the right ontologies for cognition to start with, right? So instead of taking for granted the functional categories that we have and task categories that we have and the implementation categories that we have, and just try to find ways to, make them map, we should actually question what those categories should be to start with, and how they relate to each other. So in each ways, task categories relate to specific cognitive categories and specific implementation categories, and so on and so forth. So it then became very philosophical, at least part of this debate became very philosophical. So questions about, well, what cognitive functions are really there, right? So it might well be that taking the cue from our everyday concepts is the wrong move, right? So it may well be that our folk psychological intuitions about the or the capacities that we have are misleading, at least to a certain extent, right? And so that we shouldn't actually try to save those kinds of categories at all when we are doing cognitive psychology or cognitive science more generally. So that's an option. So there we can be more or less conservative in relation to folk psychology and more or less revisionist about those concepts. And we can ask the same question about cognitive tasks. So what cognitive tasks are there that organisms such as ourselves are supposed to be, to have evolved and to develop to solve or to be able to solve? And then there is the further question of the mapping. So even given a certain, ontology of tasks and ontology of cognitive functions, how do we relate specific tasks to specific functions? And then there is the further question that is closer to how the whole thing started, namely, what are the right structural categories for brain implementation? So we already heard today about the importance of anatomy and things like population coding and stuff like that. So these are all debates that are part of these discussions. And of course, there is a further question, well, how do those structural categories relate to cognitive functions, right? So how do they, is there neural reuse, for example, as people like Michael Anderson have proposed, so that we have many-to-many mappings between structure and function and so on and so forth, or not, or, Friston and Price are right that we have one-to-one mappings, etc., etc. However, I'm not going to go into those last two things. I'm going to be interested only on the first pass of that, that graph I showed. So on the task ontology and the cognitive ontology. So I'm going to leave out the neural or implementation ontology discussion from this talk. So I'm just going to look from cognitive function to the left. No, sorry, to the right. Yeah. No, to the left. No, to the right. Sorry, I'm getting confused. So it depends on your frame of reference, but you got my point. Can we do something similar when it comes to large pre-trained models? So can we apply, any of these, ideas to those? So we've seen that we have benchmark tests that are a little bit like, measures of performance in behavioral experiments in cognitive psychology, and we have some work, limited, but anyway, some work on mechanistic implementation, right? Which is somewhat akin to neural implementation, if you wish. And interesting, there are also some of the same methodological problems appear there as well, but I'm not going to go into that here. But anyways, my point is that there is an interesting analogy when it comes to the epistemological challenges that we find when we tackle these large pre-trained models, like the large language models that we have today, and the challenges that we find when we talk about cognitive functions and so on in biological organisms. So that's what is going to sort of motivate this idea that, well, one way to go is to try and develop functional ontologies for these systems. So something that stays in between the mechanistic interpretability work and the benchmark measures. Of course, talking about cognitive might be somewhat problematic when it comes to AI systems, depending on how much baggage you give to the notion of cognition. You may not want to apply the term cognition to what things like large language models or text-to-image models do, right? So it might be somewhat misleading to use the term cognitive for those. So perhaps we shouldn't talk about cognitive ontology when it comes to these systems, but something more neutral like functional ontologies. Right? So something that doesn't have as much baggage, does not bring with it, perhaps misleading ideas about what these systems are really doing, and so on. So here's the suggestion. So that that bridge that cognitive ontologies are supposed to build between performance and mechanism in cognitive science can be or should be played by functional ontologies when it comes to these large pre-trained AI models. Now, the idea is that, well, functional capacities can help us explain benchmark performance. And functional capacities, as you all know, from functional explanations and so on, they tend to be more abstract, so they don't go into all the nitty-gritty mechanistic details of things, and therefore they give us more chances for generalization with some loss of information. That's true, but in some cases that's what we want, right? We want more generalization power, even if the price to pay is less accuracy, at least to a certain extent. And we have multiple realizability in several directions when it comes to functional capacities and the other elements that I've presented. So we can have, for example, cases in which you have different functional capacities that all lead to the same benchmark success, right? So you shouldn't, or we shouldn't infer from similarity in benchmark performance that what is going on functionally in the system is the same, right? So we can have different kinds of functional capacities all leading to the same kind of success in benchmark measures. And you can also have different ways to implement one and the same functional capacity. So you also have complicated mapping between any functional capacity and the possible mechanistic ways of implementing those functional capacities. And of course, you can also have the case in which, success in different benchmarks that perhaps are even quite different intuitively are underlain by the same functional capacity, right? That's also an open possibility. So, so we have all the features here that we also see in functional explanations that we use in cognitive science, right? So the fact that different functional capacities or cognitive capacities may lead to behavioral success in ways that may be difficult to glean from just a measure of performance. We may have different, ways of implementing the same functional capacity. Say, if you take certain versions of neural reuse, you can have, one functional capacity being mapped into different kinds of neural areas, doing different computations, but that, overall perform the same function and so forth. So importantly, though, there is no explanatory independence between, these three domains, if you wish. So differential performance in benchmarks, especially if the benchmarks are, fine-grained enough, do suggest functional differences. And of course, considerations about implementation justify or lead us to infer limits or constraints on the possible functional capacities that can be realized by means of that, mechanistic system. So there are, interesting complex relationships between these three domains. So they are not autonomous, explanatorily autonomous in any way. That's not what I want to suggest. All right, so just to try and illustrate things with a bit more of concreteness. So let's take, this task that is part of the Big Bench benchmark that has been published 2 years ago, I think, 1.5 years ago. So one of the subtasks that we designed for this part of the benchmark is the following. Oh, well, I forgot to mention. So the general theme of this of our task in the benchmark is to probe the capacity to successfully do conceptual combinations. So to do semantic combination of concepts, things like, pet fish and city tomato and things like that, right? So pet fish, as you know from Fodor, right? It was one of the famous and favorite examples that Jerry Fodor used, against prototype theory, in his arguments against prototype theory. He'd say, well, take the concept pet fish. Pet fish, if you take just the prototype for pets, well, it has little to do with fish, right? You're going to think about cats and dogs. And if you take the prototype for fish, it's very unlikely that you're going to talk or to think about good fish, right? You're going to think about other kinds of fish, perhaps tuna or salmon or not, right? But when we hear pet fish, we immediately understand, right, that we are not talking about tuna or about dogs and cats or anything like that, but that we are talking probably about small, colorful fish that that can live in an aquarium and that humans buy and flush and things like that. And we wanted to probe this sort of capacity, but of course, since these systems they are trained with an amount of data that is unimaginable for us, all of these concept combinations like pet fish and city tomato and so on, they are very likely already in the training set, right? And we want to train for the capacity to understand them, like in a way that is not just a memorization or an appeal to things that are already there in the training set. So what we did was to just invent words. So we invented concepts and we provided definitions of those concepts and then asked questions about what would they mean when combined. So here there is an example of one version. We have several versions with absurd physics and stuff like that. But this is the simpler one, in which we take a new word that we invented, like binna, and we provide a definition of it, like any animal that is furry and has 4 legs, and the word pam, and we define it as a simple sort of dwelling. And then we ask the system, which of the following sentences best characterizes binna bams, right? And then we try to design the possible answers in ways that would, try to trick the system. So to make sure that it's forming in ways, if it succeeds, in ways that are really, at least that's what we hoped, driven by the conceptual combination capacity or semantic combination capacity rather than something else, such as statistical frequency and things like that. So it was a multiple question task, and then we had several options, like these ones that you see here. Now, very interestingly, when we designed this task, it was almost impossible, or it was impossible for all the existing large language models that were available at the time. So GPT-3 and the other LLMs of the same generation, they failed miserably. But very soon, and even before the task was published, and starting from Palm on, and then of course with GPT-4 and so on, even more, they get human comparable performance in this task across the board. So they get about 80% right, which is pretty much the same that human annotators get right. Which was somewhat frustrating for us because, you know, our whole idea was, well, let's come up with something that is difficult and is going to, you know, keep being difficult for many years ahead, but it lasted a few months and then it was already solved. And then, of course, there is a question of how. And interestingly, and this is somewhat an aside, this is one of the tasks in Big Bench for which there was a huge jump thanks to the size of the network. So you see that networks that are relatively small, they all fail miserably. And then as size increases, you see the jump. So there seems to be something that emerges with this increasing size, even though there is a recent paper putting some doubt into how much of a leap there is rather than something more gradual. So this is still a matter of some controversy. But anyway, size seems to have played an important role here. But then, yeah, what does this mean? So in other words, what does success in the benchmark mean? And then we can ask, well, what tasks does the benchmark really involve? Of course, we designed it with one task in mind, namely conceptual combinations. And we tried to design the task such that we thought the system must employ this in order to solve the task, right? But is it really the only possibility? So are there perhaps other capacities that are equally able to explain, you know, behavioral success, or in this case, benchmark success at our design tasks? And then, of course, there is the question of implementation, which is not going to exercise me here. What other options might we have? So let's just, you know, think a bit about this. So one hypothesis, which was our hypothesis, somewhat implicit hypothesis that we didn't really question, is, well, they solve this task by means of doing semantic and syntactic linguistic composition, as we think humans do, right? So plus, you know, using world knowledge, right? So pet fish, for example, you cannot really infer lots of things about pet fish just by a knowledge of pets and a knowledge of fish. You also have to know things about the world, what people tend to want to have in their houses, and what people, you know, buy, what kinds of things are allowed, what kinds of fish are allowed to be put in aquaria, and so on and so forth, right? So there is lots of world knowledge that is relevant for this capacity. So let's try to do one functional, or provide one functional story here. So you might think, well, the first step is, well, replace the invented words, in the example Biene and Bam, with their definitions, right? So furry animal with 4 legs and simple sort of dwelling. Then you access the concepts or the definition or you know, prototype concepts or whatever that are associated with those definitions, and you compose them together. Then you access the relevant knowledge that is going to come from those definitional concepts. You recompose the semantics of the definition, right, with this further information you get from world knowledge. Then you infer the meaning of the conceptual combination, and you choose the answer that is compatible with that meaning, right? So that's a functional story about how they may have solved this benchmark task. But it's not the only one, right? So there is another one, which is more associative and non-compositional. So, for example, for each invented word, so Biene and Bam, you just focus attention on what follows the word means, right? And then you just embed the representations of what follows means into the representation of the new words, the invented word, like Bam or Biene. Then you merge the two representations, right? So you again embed them together. And then what you do, well, we just are going to be moved into a certain space, you know, in the semantic space of the network. And then you can look at, well, what is inhabiting the close by space in this, new space that the network has come to inhabit. And then you can assign probabilities to each one of those associations by means of the strength, the number, the proximity in this, multidimensional space, and so on and so forth. And then you just choose the answer with high probability, right? So here we may have a functional story about how we can solve those tasks without anything that is, strictly speaking, compositional, either syntactically or semantically. So the question of what tasks really did our benchmark involve is much harder to answer than we had originally hoped for. And so how to really assess the success that large LLMs, current ones, have in this task is far from clear, right? So we cannot just infer that they can do conceptual combination or semantic composition because they succeed at this hopefully very well-designed task, right? Just because there might be, the task may be probing not only conceptual combination or semantic composition, but also other possible capacities. So it can be solved by means of other functional means. So we have an unclear answer to both questions. And that's all to say that, this should be a cautionary note for us that lacking, this sort of well-justified functional ontologies for the systems, we cannot really say much in many cases in which we see, seemingly impressive benchmark success. Because different tasks and functional ontologies may apply to different systems. So something like hypothesis A, the semantic syntactic composition one, might be the right one for humans. Likely it is. And something like B might be right for LLMs, right? But if we don't pay attention to these issues or to the nature of these functional ontologies and how they may have different and complex relationships to constructs on both sides of that graph, then we may be misled into making inferences for which we don't have enough grounds. Right, so some concluding lessons, if I'm fine or not. I can run. And just my claim is that understanding AI is helped by appeal to cognitive ontologies, and that and this is something extra, that the challenges that we find that with task and cognitive ontologies in human cognitive psychology or even comparative psychology are perhaps even trickier when it comes to AI systems, because they have very different features, at least in part, to biological organisms. So they undergo very different design pressures, or even if you wish, historical pressures. They have very different learning regimens. And also, interestingly, it's unclear, this is somewhat less clear, but we have reasons to believe that the modes and degree of integration between different capabilities that they have is different from what we find in, say, mammalians, for example. So it becomes very risky to rely on human categories and or intuitions when it comes to assessing what it means for these systems to succeed at these benchmarks. And my point is that we need to try and develop something like these functional ontologies to try and help us think about this. And it's very likely that these ontologies are going to be alien in the sense that they're going to be very unlike the ontologies that we have for biological organisms. So, and here as well, I think that there are lessons that can be taken from fields like comparative functional psychology. People have been talking a lot about octopuses and all the different categories that we might need to apply to them. And I think something even more extreme might be the case for these AI systems. All right, so I'm going to skip this part because of lack of time. And thank you. Looking forward to your questions.
And over here.
Thanks. Yeah, thank you. I love this whole talk that you gave, and one thing that comes to mind is an analogous concern about the shape of some debates in cognitive science about things like language of thought hypothesis, which has recently like become even like it's kind of resurfaced as a prominent theme, where some of the people engaged in this debate, they as far as I can tell, they appeal merely to behavioral evidence, and then they try to draw inferences to cognitive architecture. And by the kind of argument that you gave today, that's definitely insufficient. You know, like the behavioral evidence underdetermines the cognitive architecture. So you really need strong assumptions about what cognitive architectures are plausible to draw these inferences, and those assumptions are themselves questionable. So it seems to me that there's a parallel to your argument for debates about cognition that some people still have not absorbed. Even though, I mean, this kind of thing has been debated for many decades, but you're sort of applying these considerations to large language models in a very insightful way. And I just want to point out that there seem to be people who have yet to appreciate the challenges here, even when it comes to human cognition.
Yeah, no, that's totally the case. And one of the I think interesting things about AI and a very, very great philosopher of AI, Cameron Buckner, has been insisting on this as well, is that looking at current AI systems also help us not solve, but at least they provide quite some evidence that helps solve or helps reinforce certain philosophical positions over others. So you're talking about the language thought hypothesis and so on. So there was this whole debate in the 80s between Fodor and Pileshin and Smolensky about exactly whether connections networks would be able to do things like composition, right? And Fodor argued, and Fodor and Pileshin argued, no, right? You need something language-like in terms of representational system in order for this to be possible at all. So connections networks will never be able to deal with this sorts of tasks, right? And now we see that, well, they actually are able to deal with these tasks at human level, sometimes at superhuman level. So what does that mean for that debate, right? So one, I think, very natural conclusion to take is that it has just been empirically refuted, right? That what we thought empirically refuted, the idea that something language-like, in the way that Fodor and Pileshin thought, so atomic representations and so forth, is just not needed, right? It's not necessary for those kinds of abilities. So I think this is another thing that is interesting about the relationships between cognitive science and AI, is that we can also use AI, to put those philosophical ideas to the test, right? And see whether those arguments from the nature of the task to, well, therefore it must be done this way, whether they really hold or not, like in the case of the language of thought and, compositionality and so on. And of course, here I said, well, that hypothesis A, the semantic syntactic composition, perhaps is true of humans. And I just said perhaps, because we shouldn't take for granted that this is the right story for humans either, right? And even if it is, it might not be a purely internalistic cognitive story, right? So it may depend on the fact that we have an external linguistic system that we can then employ for these sorts of tasks, right? So it may well be that we also solve this in ways that are not too unlike, the associative method, at least if we are not, helped by this external symbol system that we have that has these compositional features that is language, right? So I think, all of these things are brought even more into relief by looking at these systems and how they may be able to solve those tasks in ways that are very unlike what you thought were the ways that were necessary for success.
Can I ask the question? So we discussed, there was a slide with the yellow table with the cognitive capacities, the common sense construct, and then how we scientifically divide them into sub capacities that are more, which are kind of the cognitive ontologies, right? These are the divisions we do, and we assume that we have those sub capacities. And an important thing in this process of deviation relies on two things: on dissociation and variation. Because how we discover that we have different kinds of memories is because people were injured and they could perform in one kind of memory and in the other they could not. And also in normal population, we have variation between the subcapacities. And this is when we talk about one system that we all have in different equations, in different brains, different phones. We carry the same kind of system. And when we talk about AI system, then in your case, there wasn't the dissociation, right? Because the AI could perform tests. And the problem is that we don't have one single cognitive system, but each innovation in these technologies creates a new kind of cognitive system that we cannot compare. We cannot compare the old failures system that failed with the new system, because it's a different one, right? So I think that this is the challenge that really salient and underlies what the situation you described.
Right. Yeah. No. Great point. So, for what regards the first points you made, so there are some methods beyond the typical mechanical interpretability methods that can be used and have been used by people that are pretty much the same that are used in neuroscience. So you can do ablation studies with these networks as well, right? So you can just knock out a layer or some of the nodes and see what happens, right? How this affects the performance of the system, right? And of course, it's much easier to do that with these networks than with biological networks for obvious ethical reasons, but not only. So these methods, they are another way in which we see, at least to a certain extent, scientific work on the nature of these networks mirroring some methods that come from the neurosciences, actually, such as these ablation studies. For what regards the problem of multiple systems, that's definitely the case. One thing is that it's the same architecture, right? So GPT-3, GPT-4, and PaLM, and so on and so forth, they all have the same basic architecture, namely the transformer architecture. But everything else varies. So the size, how many layers, the training input, and well, they also share, most of them at least, the loss function and stuff like that. So they also share, the sort of task they are pre-trained to succeed at.
The relationship between us and other species, right? That we
might be, yeah. Yeah, it's difficult to do an analogy, but yeah, if you have something like, it's a mammalian brain, but it's a cat versus a human or things like that. But analogies can be shaky here, but it's definitely a problem, and even that is a question that is difficult to answer. So why did size matter so much for so many of these benchmarks, right? So why 5 million parameter network failed miserably at this task, and 2 billion, or no, rather 20 billion parameter network succeeded so well, right? So we don't know, right? So people started talking about emergent capacities to talk about these capacities that just seem to come from size, but we don't really know why size matters there. One worry is that it might be a matter of memorization, right? With more parameters, you can memorize more, but we have lots of tasks that show that that's just not impossible, just not possible, because they are tasks that probe things that could not possibly be in the training data. So something more is happening there, and it's unclear what it is. Of course, just to be clear, I'm not saying that they are doing anything particularly fancy or dangerous, so not singularity stuff. So nothing of the sort. I always feel like there is the risk that when I talk about, complex capacities of AI, people might think, oh my God, he's like with Bostrom and Kurzweil when the singularity is coming. No, nothing of that, right? Just to be clear. But yeah, there are very interesting, I think, scientific questions that arise that are not unlike the questions that arise in comparative psychology, but they're made even trickier, partially for the reasons I mentioned.
Similar, like sounds like why I asked, but fascinating. Thank you. Any more questions?
I was wondering about the part of cognitive ontology, because that reminds me of Monty Python and the Parrot. But I think it's not resting. Cognitive ontology is dead, and what is dead the one thing is that it required a lot of manual effort. That was a huge process that needed very careful construction. And doing that is an immense task that cannot really be taken very easily. So it's, of course, you might say it's resting, maybe another copy of Protocol will come and it will. But I think it tells you that it's one of these verify projects, and it cannot be done by a human engineer, and that something that we should worry in the context that you want to use that. I mean,
right,
if we need the LLM to construct the cognitive ontology, then
right, good. So yeah, two things there, right? So one, I agree with you that one aspect of the cognitive ontology debate, the one that I found least interesting, is pretty much that. The one that tried to, for example, scrap data from all neuroscience papers, and from that build, the ontologies on the basis of the relationships that you could find on that. I think that kind of project was not very interesting to start with, if not for sociological reasons, perhaps. I think that the more interesting one is this more deeply theoretical one about, putting into question the categories that we use and trying to come up with better ones. And this is a more purely theoretical one that doesn't depend on, annotating neuroscience papers, because neuroscience papers are very likely going to be buying into the existing ontologies, right? It's very unlikely that they go and revise them in any important sense. So I don't think those kinds of projects by people like Yarkoni and so on are particularly interesting. And I agree, that's pretty much dead. And I'm okay with the fact that that particular parrot is dead. But for what regards the second part, I think this is it's a very interesting thing, right? Because we do know that these systems are extremely good at finding sorts of patterns, right? And this is exactly what we have to try and find when we're talking about the sorts of ontologies. So they do seem a great tool to do that, right? To look at least, how possible ontologies, right, that can explain certain or a certain range of success in benchmarks. as far as I know, that hasn't been done, but I think that, once you go in this direction, there is some work that has to do with, well, we have to theorize and think about things and perhaps take some things from comparative psychology and so on. But some of it is just, finding patterns that are very unlikely that humans can find, unaided by these automated systems. So I think that would be a very promising way to go.
Thank you, Dimitri. Could you go back to hypothesis B?
Yeah.
Okay, okay, so you say it means yeah, so my suggestion was that maybe, the whole thing of cognitive ontologies might not be relevant to LLMs because they are, in a way, not cognitive systems. So, so the whole thing about talking about the meaning and other things that we do with cognitive systems might not be relevant here. Maybe you have, you have the behavior, you have, as you said, something emerge or something like this. You have the statistic dynamical system. This is the behavior, and that's it. Like, like you explain a dynamical system, and the whole thing to try and find things in between might not be relevant. Not that I necessarily believe in it, but this is just a sort of a worry with this methodology. Yes.
Right, that's a good point. It does, however, clash with some results that we already have, right? So if we look at convolutional neural networks, for example, we do find location-independent feature detectors by using things that are very much like neuroscience, like looking for the stimuli that most activate a certain node. We find that it responds mostly to, completely unintuitive but very specific kind of a feature in the input. Or if we look at LLMs, we can build semantic maps, and we see that there are some relationships that have the same metric distance between them. Like a classical example is man, woman, king, queen. Right. So there seems to be something that is, so an explanatory level, if you wish. I don't like talk of levels, but anyways, for us to understand it, an explanatory level that lies in between, the pure, seeing it as a dynamical system and just looking at the fullness. But of course, it's a sort of methodological bet. I do think that we have good reasons to think it's a good one, but it may turn out to be not the most fruitful or useful or anything like that. But you can say the same about humans, right?
Yeah.
So it's also the representational computational approach is also sort of methodological batch. Like we have lots of reasons to think that it's a good bet, but lots of people think, or some people think that it's not, right? So it's also an open, well, relatively open question. So that's another way in which, at least I think that lots of these current debates about these systems have lots of shared features with, debates that are familiar to us as philosophers of cognitive science.
Right. No, just I'm saying that the danger is that because it works with humans, it doesn't mean that it will work with the LLMs. Yeah.
Yeah. Exactly.
Your reply was good, but this was just the worry that.
Definitely. We should definitely be very careful with that. As I mentioned, we do have some reasons to think that there is a mid-level there, so to speak, as well. But we definitely should not think that explanatory level is going to be like, the one that we have in humans, right? Or in other, animals. That's definitely the case. But yeah, I don't want to say that, LLMs and large pre-trained models are cognitive systems in any fancy sense of the term. That's why I move away from cognitive ontologies and talk about functional ontologies. to avoid that kind of worry, right? So if you have a very weak understanding of cognition in terms of, I don't know, complex information processing, then they are good candidates for that. But if you require more than that, then of course they are not cognitive systems. So I don't want to take a side on that particular question. So that's why I go for functional ontologies.
Thank you very much.
Yeah, thanks. Thanks everyone.
Okay, our next speakers are Jens Harder and Robert Chagrin, Jens from Witten University, and one is from the Hebrew University.
Thank you. Thank you.
Thank you.
Okay, so this will be a very speculative talk, so as you can see, but what we will do in this talk, we will focus on a solution to what I call the sensitivity problem or arguments against the causal relevance of the mental content. And in our solution, we rely on what we call computational indeterminacy. In general, our project is to see how computational indeterminacy can be deployed to address mental causation, because usually people rely on another feature of computation, which is multiple realization when addressing mental causation. So the difference, to remind you, in multiple realization, the same formal structure can be implemented in different physical states, and here the same physical system implements different formal structures in a way. It's a reverse. Okay, so what we do, we'll say what is the sensitivity argument, then very briefly about computational indeterminacy, then a proposed solution, and then Jens will try to further address the first steps towards the famous exclusion problem. So what is the sensitivity argument? So just in large is that, in brief, is the claim is that, look, computational processes are sensitive only to the syntactical formal properties of that representation, not to their content. Think about the Turing machine. It will produce basically the same strings, no matter whether we interpret the strings, we use a binary interpretation or decimal interpretation. It is irrelevant to the result. And therefore, if we think about cognitive processes as computational processes, this will mean that the mental content is causal relevance to the output, the behavior. And more precisely, we can take the neural mechanisms that underlie cognitive capacities and behaviors like computation. Then the premise I just mentioned, computational processes are sensitive only to the formal or syntactic properties of representations and not to their semantic properties. But then P3, if computation is not sensitive to content, then content is causally irrelevant to the output of computation. P4 from P2 and 3, content is causally irrelevant to the output of computation. And from P1 and P4, maybe with some other assumption, what mental content is causally irrelevant to the output of mental computation and hence the cognitive capacity and behavior. Now, many people either deny the first premise P1, others deny the second premise P2. They try to say that computation is sensitive to semantic properties. We actually will focus on premise 3 and try to undermine it. But before this, just maybe 2 comments about the main premise, premise 2. So one thing that I already mentioned is that notice that the premise is about computational processes in general, not just the mental processes. And so from P2 and P4, the whole inference here is not pertinent just to mental content, but to end content of the computations, even in the laptop. Moreover, it seems that we are less alert to the conclusion that the content of the states in our laptops are not causally relevant, but we are very anxious when we are told that the mental content is causally irrelevant. Another comment is that notice that in P2 we have a positive and a negative claim. The positive claim is that the computational processes are sensitive to formal or syntactic properties. The negative claim is that they are not sensitive to semantic properties. Still, also notice that only the negative claim is relevant to the rest of the argument. But still, almost always we see the claim go together. So here are some examples from Fodor. Computational operations consist entirely of transformation of symbols. Something is missing is, of course, performing those operations. You can't read there. Anyway, they have no access to the semantic properties of the presentation, including the property of being true, etc. Block says that block any Turing machine can be constructed from simple primitive processors such as AND gates, OR gates, and the like. Gates are sensitive to the syntactic forms of representation, not to their meaning. Francis Egan says computational operations are sensitive only to formal, i.e. non-semantic properties of representation over which they are defined, not to their meaning, etc. So one could ask why having these two claims together. And one answer is that maybe it's some sort of an exclusion claim, since computational properties are causally sensitive only to the formal or syntactic properties of representation, so they are not causally sensitive to the semantic properties. So it meant to say something negative about the semantic properties, imply they're causal irrelevant. But what I want to suggest, and here we will digress a bit, is that actually this premise meant to say something positive about about the content, about semantic properties. And the claim is that actually computational processes can support semantic relations, that even though they are sensitive only to the syntactic or formal properties, they still they support semantic relations. And just to mention it, we should remember that the roots of non-sensitivity is from logic, and their proof theory that we can have derivations or proofs that are sensitive only to the syntactic or formal properties of the formulas, but still they can preserve semantic properties like truth. This is a very famous quotation that I like from Gödel. He said the outstanding feature of the rules of inference being that they are purely formal, refer only to the outward structure of the formulas, not to the meaning, so that they could be applied by someone who knew nothing about mathematics or by machine. A few decades later, Fodor famously says something similar about machine, about the Turing machine, how they can preserve semantic properties like truth. So he said, well, as Turing famously pointed out, if you have a device with operations or transformations of symbols, and whose state changes are driven by the syntactic properties of the symbols that it transforms, it is possible to arrange things so that in a pretty striking variety of cases, the device reliably transforms true input symbols into output symbols that are also true. So again, the Turing machine, even though it is sensitive only to the syntactic properties of the symbols, it supports semantic properties like truths. For Fodor, this idea is revolutionary for cognitive science and also for others. I think that the reason is this, since probably the 17th century, maybe before, people think about the mind, brain as a representational system, a system that transforms representation. We can think input representations to output representations, but still the processes themselves are internal. So, and the semantic properties, many people think of them as having to do at least partly something with the external world. So the question, how these internal properties, right, internal processes can get us to the right representations. And the answer, I think the whole thing about computation is that it shows how to do this. If neural mechanisms are computing mechanisms, then the internal mechanism, even though they are sensitive only to the syntactic or formal properties, they preserve the semantic relations. Where I think Fodor was wrong, he thought that this is applied also other thought like Ramsey only to classical machines, but as me and many others showed, it is the same idea is very widespread also in computational neuroscience. So all this digression was first we did it for two reasons. One, to show that actually we have good reasons to accept P1 and P2 and not to reject them. Again, and the other one, and because computation that are sensitive only to the formal properties, actually they serve a useful purpose. And the second reason is, as I mentioned before, I mean, the second premise does not mean to show that mental properties are epiphenomenal, but actually to show that you can support semantic relations by doing computation. Still, of course, there is the worry that if computation is not sensitive to content, then content is causally irrelevant to the output of computation. And the question is now what to do about this premise. So let's again think about the non-sensitivity to semantic properties, and think what does it mean? So we started the talk by appealing to this intuition that many people appeal to when they talk about non-sensitivity, that my pocket calculator is sensitive to the shapes of the zeros and ones, not to their interpretation. We could change the interpretation from decimal to binary, and the computational process would be just the same. So if we take this intuition and make it more precise, so we can say that it's followed that P is a physical process, a system like a laptop and a brain that implements a computation formal structure F that proceeds from input representations I to output representations A. Let Fi be the formal properties of the input representation I, and let Fo be the formal properties of the output representations O. Let Ci be the content of I, and Co be the content of O. Given all this long introduction, the non-sensitivity claim comes to this. It says that changing the content Ci of the input representation of F will never alter the formal properties Fo of the output representation of F. We get exactly the same output strings. Okay, so this is non-sensitivity. So my answer is here. The causal irrelevance of content, it seems that it says something like this: the content CI of the input representation of F is causally irrelevant to the formal properties FO of the output representation of F. So the string will be the same. Now, but how we get from NS to CIC, which is the third premise. So we have to say something about causal relevance. Well, causal relevance is a murky issue, but if you want to get from NS to CIC, at least you have to accept the following condition. That says causal relevance, that content is causally relevant only if some change of the content CI of the input representations of F alters the formal properties FO of the output representation of F. Namely, if you add CR to NS, then you can infer CIC. Okay, so I'm not going to defend this condition of causal relevance because this is really what you need to make the inference from NS to CIC. Okay, so this is the justification of the condition. Otherwise, you simply can't establish the third premise. Okay, now, but how can we now block or undermine this this inference? So some people like Fodor himself and also Peacock, they say, okay, it's true that the content is causally relevant to the syntactic properties, but it can be causally relevant to the content of the outputs, right? If we change the interpretations of the input, we change the interpretation of the output. We don't like this route because the changing of interpretation, it's not clear how it is related to the causal process itself, but we will leave it aside. We will take another route. What we will say is that actually when we talk about changes of content, the non-sensitivity claim and the causal relevance claim actually refer to different sets of changes of content. One set of changing of content is that what we do is that we take the same formal structure and, as it were, change the content of the states of this formal structure. In this case, I think indeed the formal properties of the outputs will not change. However, there are cases in which a change of content results in different computation at all, in different formal structure, and in particular in different formal properties of the output representations. So what we will say is that the non-sensitivity claim actually refers to this kind of changes, whether the causal relevance should take into account both kinds of changes. But if this is the case, you cannot infer the causal irrelevance from non-sensitivity because the assumption is that non-sensitivity and causal relevance apply exactly to the same sets of change. Okay, so okay, computation. So to do this, to show this, we appeal to the computational indeterminacy. So you know this example from yesterday, from before, of this tri-stable gate. And instead of voltages, we will talk about the high, medium, and low. So one way to think about the functional organization in this table, But we can also group the high and the age and the M together, and then the as one group, the L as the other group, or the M with the L and the H differently. And what you get here is really different functional structures. You can see that there are, you can see here it should be it is B, not A. Okay, maybe.
You can shrink that little window.
I'm not sure I want to make sure because it's someone else's, it's a.
Oh.
It's a Zoom on someone else's computer.
There's a
So
computer inside the
someone-
table, so
Yeah,
that's why.
so someone
Oh.
else.
Okay, okay, and if we interpret, if we label the A's and the B's with 1 and 0, or with 2 and 4, this, here we will get the O function, and here we will get the ZO function, okay? So, okay. Now, okay, there is, we saw yesterday, we will see tomorrow, there is a lively debate about how to resolve indeterminacy. I will not, we will assume the semantic view of computation without argument, we will not get into this argument. I just want you to notice that the semantic view has, the question is, in a given context, why should we choose this computation and not this this structure and not this structure to be the computational structure of the system? And the semantic view has a very simple and elegant answer that you don't have to accept, even though it's true. And the answer is this: look at the content of the physical states. Okay, if M and H as one kind of content and L as another kind of content, simply group the states this way. And if H is one kind of content and L and M have another kind of content, group the states this way, and then here you will get ZO at the end, and here you will get more. And this is the solution, and at least it works in many cases. As said, we will simply assume it. We will assume that content determines the formal structure, which is the computational structure of the system in a given context. And what we now want to claim is that this determinative role, we can also think about it as a causal role of content. So this is the idea. Okay. So our proposal, I have 7 minutes and then I, okay. So our proposal is this, just to repeat. We said that the tests for causal relevance and non-sensitivity are changes of content, what happens to the output strings. And we say, okay, distinguish between two kinds of changes, what we call uniform and non-uniform changes of content. We will say that uniform changes do not alter the formal properties of the outputs, but some non-uniform changes alter the formal properties of the output. Then we will say that the non-sensitivity refers to non-uniform changes of content, and hence is true. But CR should refer to both kinds of changes, uniform and non-uniform. And if this is true, then you cannot establish the third premise for non-sensitivity to causal irrelevance of content, since NS and CR apply to different changes of content. So this is the argument. Okay, you still follow? Okay. So what is a uniform change of content? Uniform change of content, as mentioned, you can think of it as just taking the same functional structure and simply change the content. If the content was or here age was moved, M was the content of M was moved, the content of L was don't move, then changing the content from move to press, but do it uniformly, namely M, you change to H and M one kind of content by another kind of content, and L with the second kind of content to the second kind of content. Then in this case, really, you will not change the computational structure of the system. You don't see it, but here it was O, and it stays O. Okay, so there is really no change here, and we think that this is what people mean when they talk about non-sensitivity. Yeah, that if you take the same formal structure, you just change the content of the state, as it were, the formal state, then the output result will remain the same, which is exactly what. But there is another change. There is another change of content. The other change of content that we call uniform, while in the environment one, the content of M was lumped together with the content of H. In environment two, we didn't just change the content, but the content of M now goes with the content of L, not with the content of H. In this case, what this will do, this change of content, will also change the formal structure of the system. And so the computational structure in this environment will not be this one, which is OR, but will be this one, which is the basis for ZOR. So we see that some changes of content also change the computational structure of the system. Now, the next question, but why causal relevant should care about non-uniform changes of content, right? And we think the rough answer is that what you change also by changing the content, you change the formal function that is causally relevant to the task. So in environment one, if the task is like moving the arm or something like this, and so computing OR is the causal relevant function for the task, whereas performing ZOR is not causally relevant. The system that implements OR without another system that implements OR without implementing ZOR would perform the task of moving just the same, whereas a system that implements ZOR without implementing OR will fail to achieve this task. In environment two, where the task is pressing, so the formal function which is causally relevant is ZOR and not OR. Just to show it in maybe this, if we connect the formal function to some motor arm and to movement, so here we will say, yeah, the formal function that is relevant to the movement of the arm is OR and not ZOR. Okay, and while in the second environment, and the formal function that is causally relevant to pressing is ZOR and not OR. So we have some indication at least that that the non-uniform changes are something that the causal relevance condition should take into account, not just the uniform change. This is all we wanted to show. Okay, so recapping. Non-uniform changes of content alter the formal properties of the computed function from OR to ZOR. Why this is relevant to the causal relevant condition? It seems to be causally relevant because these changes of content also alter the computed formal function that is causally relevant to the task from OR to ZOR. This indicates that the content makes a difference to the causally relevant computed function. So we have an indication that CR should take into account also non-uniform changes of content. So basically, so this completes the argument. The third premise was for non-sensitive to non-sensitivity to total irrelevance through CR. But as it turns out, non-sensitivity and CR apply to different sets of changes of content, and thus you cannot make the premise. So this was very quickly. I left you exactly.
Time.
So if you think that this was wide and speculative, so just wait.
So as you know, the debate on medical causation is huge and it really mushroomed since the 90s and still publications ongoing and various problems have been formulated in this context. So probably the most widely discussed ones are the sensitivity problem and the so-called exclusion problem. There's more, there's the supervenience problem. There's also the problem from within and other problems. Now, I personally probably won't believe all of these formulations have an inner connection, even on the surface of it, they don't really seem to have that. So here is an attempt to think about what we just presented to you could have as an indication for the so-called exclusion problem. So the exclusion problem is often formulated in the following way, at least for now, out of the blue. Mental events such as desires, beliefs, and physical effects. Mental events are not identical to physical events. Every physical event, including behavior, has a sufficient complete physical cause. Mental events will not double cause physical effects. Under these certain formal interpretations of these sentences, we actually get an inconsistency of these claims, and therefore we have a philosophical problem. What's often left out, and I have read a lot of this debate, and I can tell you it's a bit of a mess. So people use different concepts in different words, and often they leave out this what I believe is still in the background of most of these claims, namely that mental events have their effects in virtue of their representation of content. I think that's left implicit most of the time, but still a thought. And furthermore, physical events, of course, have their effects in virtue of the physical properties that they have, not in virtue of potential further mental properties that they have. Okay. So this is, as I just said, often left out and implicit, overlooked. But once you add it, you can immediately see there is something going on here that sort of has two different kinds of causal relations that are discussed in the first place. So one is sort of mental causation to a physical effect, and here's physical causation to a physical effect. But these can be sort of causal relations in virtue of different properties. Okay, so that's fine, but the question is, how can we make sense of this? Okay, can it still be true? So is this still a contradiction, or can it be actually can this inconsistency be resolved? So here's again this first sentence: mental events have physical effects in virtue of the representation content. And now something we just heard in a different version: changes of content do not alter the internal physical properties of the system in attaining these states. So which actually will be causing. Do they? Okay. So here is a potential answer. The answer is no. Okay. At least in a specific way. So changes of content as a consequence of change of the environment / task can determine a change in the meso macro scale functional formal properties of the system. So that's what we just learned yesterday. We learned about the difference between slutzing and Voronin. A version of it I will just present. So different computed function means differently demarcated physical units, modules of the brain that are relevant for the behavior. So microphysically speaking, sort of the same thing still goes on, but now we sort of probe it in a different way, and we sort of demarcate the system in different ways, so it really fits with the content. Okay. And so different physical units, modules have different physical effects, or at least can have different physical effects, both short and long range. Okay, so that's sort of the lesson from computational indeterminacy, maybe combined with the semantic view. It basically means that we can sort of induce, if you like, a different formal functional structure. Did I do this?
Just happens.
It just happened. Now what?
Mental contention.
That's how do we it should be there on the screen. See that somewhere?
So your in here doesn't have like the mouse thing?
No, it doesn't. something wrong with the system. It is somewhere there's a hidden lab, there's a hidden computer somewhere. The question is where. The other option is. We can, where is it? Here we go, yes.
Yes.
Oh, finally, you can actually, yeah.
That's
Okay. It's also network causation in some sense. So as I said, the basic microphysical setup of the system remains the same, however, let's call it meso macroscale functional structure changes, formal functional structure depending on the environment. So there's some kind of an, if you like, an inducing of the functional structure, formal structure of the system by the environment and tasks. So and since the functional formal structure is quasi-relevant, or can be so for macrophysical behavior of the system, there is a way of actually understanding this assumption as correct. Many events such as desires and beliefs have non-macrophysical effects in virtue of their representational content. So that's because, depending on the content, we get a different formal functional structure in the system. And so Oren gave you this example of different motor outputs, right? So if you have, a sort of an additional gate or something that can then actually produce different motor outputs of the system, but you can even extend this insight into a situation where here this air marshaller actually has the same motor output and still causes something else. So imagine the following. So here's the air marshaller. The claim is that the function that the marshaller computes is ambiguous, so it's not locally determined. What clearly is the same is his visual input. So he sees this plane up here. He sees this plane. So the whole pixel, every pixel is the same. Okay. And also the brain dynamic, physically speaking, is the same. So the immediate behavior here is also the same. However, there is a different function computed by the marshaller depending on the even broader environment. So the idea is here that what he does is he lifts the arms, okay, but there's two ways you can understand it depending on the overall environment. One could be a signal to the blue plane saying, come and face me. Okay, so turn so that you face me. The second one could be a signal to the red plane, fly upwards, otherwise it's going to crash into the tower. Okay. So maybe if you don't face me straight, then you're going to crash into this little car or something. Okay. So and so in the first environment, it's actually the case that the stick trowel, so the fact that they're sticks and not round, that is the crucial signal. If you lift those up, it's a crucial signal for the blue plane to come facing you. In the second environment, the crucial part is that we have red trowels here instead of green. And so lifting up the red and green trowels means go up, fly up. Okay. So what this shows is that depending on the overall environment, even here the immediate motor output is the same, still a different function is computed. Because in the overall, you can even call it social system, there's different contents that are being associated with this kind of function, with this kind of behavior. Okay. So and you can easily see that depending on what the overall environment is, this plane will crash into the tower or not crash, or this plane will face or not face the marshaller. Okay. So in that sense, given the causation of the computation and representation will be actually different depending on the overall environment in which the system operates. So we believe that's the crucial insight for understanding vector causation. That's how it works. Okay. So, and that's a very important insight because it really makes our view very different from the most prominent ones in the debate that have been around for a long time. So for instance, here, Yadlo's paper from 1992 is still the most cited one in this whole debate, and that causation that has over 1,000 citations, the next one is for 450 or 300 citations. Him is very famous, right? But this view is also here. The subset view is quite famous. The subset view has this idea that a mental causation works by using a subset of the physical powers of a certain state. Okay, so that's what we mean. And Kim has, of course, this idea that there is a type identity between mental events and physical events, and that's how the causing works. Okay. You will notice that our view is very different from all of these, and it actually shows that all of them are wrong. Because the subset solution, he works with physical powers, right? I mean, at the end of the day, it's for the subset of our physical states, or still physical powers. It's almost eliminativist. The counterfactual solution, Gödel and these others, is wrong because, well, to say it shortly, there is actually no counterfactual dependence of P star E onto MC. We have not to go through this detail, but it's partially because of computational determinants. The essentialist solution of Diablo is not identical to this one, but sort of claims that there is an impoverished essence that MC has relative to PC. And sometimes, because we use proportionality as a criterion for causation, this impoverished essence is sometimes the better fit to an effect. Okay, but here also we would say, of course, the relationship is misconceived, because what we have here is a relationship of computational or representational state and physical state, and that relation is not one of essence inclusion. And Kim clearly is also. I'm done with this one. Thank you.
Very nice, both parts. I just want to try something here. I think that, intuitively, it's clear that if the indeterminacy of computation, so we don't know which computation is, there's no fact of the method. As to which computation is being implemented, then it seems intuitive that it will have an effect on the question of causal relevance. So I think that overall you're right, but it seems to me that when you are actually what you ascribe to change your what you call non-uniform change of content is basically a change in the physics of the system in a sense, because you are you're putting you're labeling the states, the physical states in the different ways of looking. So you're actually looking at the evolution of different what Young called different macroscopic properties of the system. So actually, you're looking at a different, the two computations are the XOR and the OR are actually the vehicles of the computations are different. The physical vehicles, the macroscopic properties, the groupings. What you call
You call it, this you call, we haven't changed this.
no, of course, but what you call different groupings.
You call it, this is the physical for your
Yes.
macro physical states.
Yes.
Yeah, so it
So I
was
think
this
that-
and now it is this.
No, but I mean, the different, the different groupings are
Yeah.
different macroscopic properties of the
Right.
of the system. So I would say that the physical vehicle of the of each of the two computations is different. And this is why it is true that
As I see here, I think there are some different views about indeterminacy, but as I see the system in a way implements both this and this, okay? Okay, but for a given task, only one is the computational structure of the system. Okay, it implements this formal structure or what you call macroscopic abstract structure or something like this, okay? So basically, in a way, they were both there before.
Maybe also I phrase.
You
it not-
just,
not
when you
optimally.
change the environment and you change the content, what happened is that the computational structure or the macroscopic structure, call it like this, that is relevant for the task is not this, but this.
Right,
Okay.
but the macroscopic structure has causal significance. Because it's like.
Yeah, I don't
it's
deny.
If you would look at, you have a given system and you look at its temperature. And you describe the changes of temperature as the implementation of something.
No.
And then you look at the pressure. And that would be a different computation. So I think that it's the same. It's the same. In two groupings here are have the same status. So you
The same status in causal in terms of.
I mean, the causal behavior.
Let's go back to this example, okay? Here, okay? Here, I would say that only what we call the O structure is causally relevant to the movement, right? The fact that the system also implements the Zork function structure is irrelevant.
Right, but yes, but it's not a change of content, it's a change of, you are looking at a different physical aspect of the system. So.
Different property.
A different physical property,
property.
so it's like, I mean, just to make it extreme, it's like if you have a certain, I don't know, system, macroscopic system, and you look at it, the way in which its temperature changes. And then there is a different way of looking at the system. You look at its pressure, the way the pressure is changing.
Okay,
These two things are physically, behave different physical behaviors.
yeah.
And then you would say that the causal structure is different here. It's
Okay.
one and the same system, but the causal
Okay,
structure.
so you offer an alternative,
No, and what you are saying is absolutely right,
okay,
Yeah.
but you are ascribing it, you call it the change of a non-uniform change of content, but it's actually
uh-huh.
a different way of looking, these
Physical
are two
properties.
different ways of looking at the different physical aspects of the system.
Okay, so I'm saying you still offer a different, you say it's all the same, but what really changes here is not the content, but the way the observer or something like this looked at the system. Okay, I will not, I'm not sure we want to go into this debate. Okay, no, so here we say, we really assume the semantic view. Yes, someone can come and say, no, it's not really the this is fair. I'm not sure.
Semantic view is
Right.
sort of parasitical, something else.
Yes, okay, so here we have to go into the debate about the semantic view versus other views that might also, by the way, the mechanistic view, that might use exactly the same move to argue, why it's not just the syntactic properties that are causally relevant. Yeah, this is fine. I mean, at this point, and now
Yes.
but the debate about exactly which properties is really a debate about the relevant, about theories of computation. We will not get into this.
Yes, and also I would say that actually what you can show here, you can get, apply to your solution. It doesn't matter how you understand it, to just to say that in the same way that you have indeterminacy of computation, you have indeterminacy of causal structure.
But here, the answer to
Okay.
this, so, I think, I think we recognize that option, but I think you still want to say that the semantic explanation is still the better explanation. So it's more about what's the more virtuous explanation at the end of the day. And one reason that we have this paper together will be saying that actually the causal process is not what's really interesting, relevant. So in your case, the solution will be to come up with a good description of the causal process that leads eventually to whatever is the outcome, right? But there could be reasons in saying that, specifying the causal process is not really the right way to go. So one reason could be, it's going to be just too complex. The other reason could be, actually, what exactly the causal process is not so relevant at the end of the day anyway. So what's really interesting, what the really relevant causal aspect here is that there is a representation, and that leads eventually to the effect, no matter what happens exactly in between. So in that sense, I think, we have to discuss this, but I think we could grant you this point and still say that the semantic explanation is the better one out of specific reasons.
Right, no, I agree, but it requires a different argument, and here we saw if the semantic view of computation is true, then you can see how content can be causally relevant, and more generally, it is an argument of how content can be causally relevant. We still need, I agree, a further argument. Yes.
I'll just interject. Rotem is very nice. We have 10 minutes and 5 questions. So 2 minutes each. Now you go.
Thank you. Okay, first of all, I wanna suggest a proper acknowledgement with respect to the subset account of realization and then of mental causation, all that. As far as I know, it's in its like explicit formulation, it's due to Jessica Wilson, who was Shoemaker's graduate student at the time, and then Shoemaker published the same idea like shortly after that, and being famous became associated with the idea. So anyway, I would just recommend looking into this and maybe acknowledging Jessica Wilson. But then on the substance, I agree that content is causally efficacious and has impact on certain kinds of computation. I don't think I'm going to agree with the way you get there, but well, there's too much to say. So I'm going to say, I would urge you to consider even more deeply the role of the situatedness of the computations and the representations together, and how computations are needed in this context to build the representations and the content in that context is a function of the computations themselves. It's not just something that we add as an interpretation, but like Marcin was talking about dimensionality reduction, that is something that is accomplished by the computation in a environment. So given a certain environment and the inputs, then the system itself has to build its own internal states. It has to accomplish this dimensionality reduction, and then it can be done in different ways, by different systems, but it's the computations that build the internal states, and then they build the contents that then drive subsequent computations and subsequent action. So something to consider as part of the story.
So you would say that computation is actually sensitive to content?
Yes.
Okay, so you are in this camp. Okay.
Well, some computations, not all of them.
Right, but by the way, it's true. We don't assume that you have that the content must be derivative. In the brain, it can be
Yes.
Original if we can. Yeah.
Yes.
But we have probably a different view. You say you have computation that beats content. For us, content actually is prior to computation. The whole remark about situated cognition, and I think is relevant, and maybe we should, but nevertheless, I think the real debate here between maybe us is whether computation is prior to content and representation, as what you think, or as we think. Actually, content is prior to computation, and we should show it here. you have content, you have physical states, and you group the physical states according to content, and this is how you get the computation. So, yeah, this is the real debate. Yeah, but this is, as I said, it's another debate. Yeah, but then.
I think this is probably in the end the question about what you mean by the formal properties of the output.
Okay,
But kind of here's the question. Here's an argument and what's wrong with it.
okay.
In order to change the formal properties of the output by changing the content, you need to actually make that change somehow. You know, in order to you know, alter kind of the groupings, you need some mechanism to alter the groupings. I mean, doing it just in your mind is not enough. Harking back to yesterday, you need a mechanism to do it. And then once that has been, those provisions have been built into the system, then you get the point that the physics is, you know, it's a different system, different cause of change.
Not locally speaking. Well, you'd say that overall some kind of, I mean, the grouping needs to be made somewhere, you know, some broader physical system or something. But locally speaking,
It just could happen. Though.
it's the same system.
It just could happen that nothing would be changed in the system itself, in the computing system. But the observer who looks at the output will look at different things.
No.
Will look on the temperature, not on the.
This is your view.
About the formal properties of the output.
Yeah, no, what, but I don't want to say, it doesn't have to be in our mind or our interpretation. It's said, it can be in the brain, and the content can be original, okay? And then, of course, you need some mechanism, okay, to change here the things. And of course, something in the physics surely must be different, right? But as Jan said, it doesn't have to be something local in the physical system itself. That's, I think, the point of indeterminacy. And you can see that if you make, you keep the local system intact physically, you can change something outside, right? In the same of the of what the system gets, how it interacts in the environment, then this might change the content, and the content now, since we don't have the Zoom, you can see that with the basically with the same formal inputs, you get a different formal outputs at the top row. Here with 1 and 1, the same system, the same physical system, the output will be 1, and here the same ones and ones, the output will be 0, and this is really what you mean.
I'd need to see a wiring diagram or something.
Okay.
To show how you know, a non-local change could
Okay.
kind of filter through and change the grouping without changing the dynamics of the system
Oh,
you
this,
depicted in your code.
this, yeah. Okay. Well, Jens, this is your task.
Kind of reiterating questions. So I think about it, you can describe the system in three different kind of levels or ways. You can talk about the context, you can talk about the syntactic functional properties, and you can talk about the physical properties.
Right.
So, okay, maybe I can don't completely understand what you mean by changing the content, but it seems that when you talk about changing the content, I think you make a good point that you can also, in some cases, change the computational properties. But it would seem that the physical properties would stay the same.
Right.
And then, so you would say, like it's not that computation determines behavior and content is relevant, but I still can see how that changes the fact that it seems that content isn't relevant to the physical, like for positive physical processes.
Right. You're absolutely right. In the sensitivity problem, yes, I mean, in the sensitivity problem, the issue is about changing the formal properties of the output. You are absolutely right that in this solution, the physical properties of the output representations has not been changed, okay? If we want then to expand it to other problems of mental causation, we have to show this in addition. Yeah, you are completely right. Yeah, in this, yeah. You want to add anything to this?
If the former properties have changed, you can think of another device that now works with the ones and zeros. And it translates those into cause and effects, physically speaking. And then so you can see that in the overall global system, actually something physical can also change.
Right, yeah, if you hook in the downstream, right? So, yeah, so you can have it also change. You can have different physical properties, yes, but here, I mean, from here to here, you can change the, but I don't want to confuse here two different problems, yeah. Okay, because here the question is about the formal properties, right? If you change the formal properties and then connect them to a motor output, then the motor output will, in the downstream can be different too. And the sensitivity problem is related to the formal properties, and you're absolutely right. In this case, the physical properties of the output remain the same.
Not much time left, so maybe opening the last and then Corey, and then we'll answer.
Okay.
I can still answer very close to the question.
My original one was too, so I'll ask the kind of silly question. Anyway, can you go back to the error marshal example? I didn't understand that at all.
Speculative parts.
Oh, okay, right.
So because the idea is to find an example where you have the same, locally speaking, the same physical goings on, but you downstream you have really different effects depending on what on the overall system. I mean, in Owen's example, there was a different motor output of the arm or something,
Right.
present movement, right? So here, in a way, the difference occurs only beyond the arm, right? The arm is still the same. This was supposed to be an example showing that you can even have locally speaking the same motor outputs, but still you have different computations and different contents being computed.
So maybe this is, I'm like reading way too much into this, but so the idea is he's got the same visual input,
Right.
he's doing the same thing, and could be, but presumably we could ask him, like, what were you intending to do? And his attention is different depending on whether he's directing the red plane or the blue plane.
Sure.
Those brain dynamics are going to be very different. So in what you said, like his brain dynamics are going to be exactly the same. That just can't be true. That doesn't seem like a good example to me of like same physical system, same inputs, same outputs, but different computation. I mean, I buy everything else you said.
It still fits because, I mean, I think it still fits because what you just now said is, you know, what if you now take that system and because we have an overall environment in which also other norms and you know norms and contents are in place, and I asked the guy, so what did you do? Then his output, motor output will be different. His mouth will do different things, he will express different things. But that's fine, because in a sense.
But wait a minute, if you parse things that way, doesn't that kind of go to the point about then you're saying that it's not different contents, it's different physical systems?
Yeah, so in some sense, yes. So because what you then will have is already in sort of the brain. I mean, I simplified completely,
Yeah,
right?
okay.
You'll have in the brain already a different sort of another gate that will then actually in a very short range produce different outputs. But this gate will still work on something that is actually identical in both situations. Okay, where the computation is, I get this input, and this is translated in some kind of in some code output or some you know some symbol output. So I see that the example can be confusing because then we immediately look
I mean, yeah,
beings and so on. I try to find an example just where it shows that the effect can be even far downstream and still become the
Right.
cause of, even though locally speaking, the same thing is going on.
I would just,
I agree.
his fundamental physical brain dynamics, I mean, that can't be right.
Let's
you know,
keep that,
because-
let's keep the only that module in focus now that actually, computes the input. Plus some kind of immediate output, which can be the same. I think this you
Okay.
agree with, can be the same in both situations, in both environments. There's at least going to be some local module in the brain that actually computes the same thing. Even though
Right.
that's output of that
Right.
thing, which is the same in both environments, has very different downstream effects.
Yeah, that part I totally agree with.
So
Just-
that,
yeah,
in that sense, I agree, it's a bit of a maybe misleading example, maybe I can think of another better one. But yeah, but in a way, it shows something very similar as the example Owen gave, hand movement, just to give the idea was supposed to be, it's even downstream, you can see very broad and clear and sort of, real life effects.
right. I think using the more complicated example made it harder for me to buy the story.
I
'Cause
get
I bought
it, I
it.
get it, so I have to think, we have to think with it, that's a good
Right,
idea
okay.
to present over you.
Thank you very much.
Yeah.
Right, we'll reconvene at 4:30 sharp.
That's what you always say.
Well, at 5:30, I'm going, I don't know about what's going on. by then.
Thank you.
I just mean the brain dynamics. So like, you know, here's something that's, I think, fascinating. So, about covert attention. So I'm looking at you, but I'm actually attending to Dimitri. And like, now I'm looking at you, but I'm attending to the water bottle to your right. No behavioral output difference. Input's exactly the same. I haven't even moved my eyes, but my brain is doing something very different. Right? So that's just what I was thinking, like, if what that guy is doing is intending to, if he's attending to the blue plane, even his, like, everything external could look the same, but his brain dynamics are going to be very different than if he was attending to the red plane. That's just what I meant. Like, there's no way that that's the same physical setup. Unless you zoom out really, really far and say, no, by physical, we mean these much more macroscopic properties. But that was the point that Mira was making about, like, well, that's not a change in content, that's a change in what you're calling, like, what I would call the physics, right? So that's just what I was getting at. Yeah.
Something more, something that.
Yeah, the covert attention thing, that's just one of my favorite examples of, like, you can tell yourself, that, like, I mean, my wife has a bad habit of doing this, like, she'll kind of look at me and then, like, her eyes will just drift slightly. She's like still looking at me, but she's starting to think about something else, but it's like, yeah, behaviorally, you can just be doing the exact same thing, but you know that you're thinking about something else, or or visually attending to something else in your visual field. But no discernible, no one would ever be able to tell, unless you're in a brain scanner, or they're you.
Maybe that's the whole idea.
So,
Right. You're right.
Yeah.
Right. This would be because of relevance, as you say, that's right. And
well, I mean, I think this point about
right, but it's a nice point, and I can think about
whether, like, how you're going
part of the
to,
diagnose why they are wrong could be that actually.
like Moron would say,
For sufficiency of the mental.
it's the same physical,
correct.
right?
Yeah, thanks.
Like physically seeing the exact same thing. But depending on how you group the physical system, is like, then you can label one thing as well as other things. Whatever the border calls that, it seems right to me.
No, but you, I know.
I mean, my point about that example is what's practicing.
It's amazing, so familiar. Yeah.
This
I
guy's
really-
thinking thing,
I mentioned, I was,
I think
a
that's.
long time ago, 2008, I was at Yale University.
So I don't know.
And I was somehow,
I was
to
assuming-
Freud inside at the time. And you came over for a talk and, So I swear, yeah, of course you don't remember that, but so I know you for a long time. Yeah, so.
I mean, like, there's gotta be something.
You know, as I said,
Yeah, but that's the point. You're right. But I think we have to find why it's really not the point. So, you're saying as well?
I'm a very.
That's how- Yeah. But you said.
Do lots of mathematics and lots of.
Yeah.
All the things I always say, but I make.
Also, yeah, I don't know. This is so much fun. I love this. It's exciting to be the top.
Chips are nice. Moves are nice.
Yeah.
Very pleased.
Yeah. And also, I mean, some of the things that we heard, maybe all this talk, it shows everyone that what some of you gonna have said when they rejected our first proposal, this we have talked about the grand proposal. So the reaction was by one of the reviewers, it's a nice thing, but it seems like it's, blowing it out of proportion.
So, I'm not thinking that it's out of proportion, I think it's, it's misspoken. And then you make, your claim is absolutely right.
Yes.
But tell them that that is
Yeah.
called.
Yeah.
And that you don't- But what all these other people are asking for is.
Nice. Thanks so much.
Okay, so our speakers now are Owen Denker from the Hebrew University and Maine Cameron from the Fine University. And they will speak about the individuation of a quantum computer.
Thanks very much. I'd like to thank first of all, Nir and Oron for organizing this wonderful event, and also extend my thanks, and I think other people's also, for our colleagues, family members, and friends who are now on the streets fighting for our future of this country, and maybe some of us will join them later. So, but my heart is with them. This is why I had to, I'm talking about quantum computation, but my heart is elsewhere. Anyway, so let's begin. Yeah, so fortunately, all of you are familiar with the problem of the individuation of computation much more than us, and for a much longer time. And each of you has their own solution or way of understanding the problem, whether the problem can be solved or not. So our task is a small one, to see whether there is an analogous problem in quantum computation. And for this, and to do that today, we held a small task of explaining what quantum mechanics is, what quantum computation is, and then present the analogous problem of the individuation of computation, or indeterminacy, or triviality, and all of this problem of this family of the problems. So for that, we have the handouts. I'm not going to go through all of these details, but we have some figures here, and we'll go very quickly over them. So, quantum mechanics. According to standard quantum mechanics, I emphasize standard because, as we'll see, there are other views, but we'll focus on this one. So, according to standard quantum mechanics, the state of the world, or the state of a system in the world, whatever that means, is formally represented by a vector in a complex vector space called the Hilbert space. And this vector, as vectors in standard vector spaces, can be represented using different coordinate systems. And the vector remains the same, regardless of which coordinate system we choose. So those coordinate systems are all on a par. And the same holds for the case of the Hilbert space in quantum mechanics.
where the coordinate systems are called bases. And in this figure, you have the quantum state C and various coordinate systems using which we can describe it. The state of the universe, the evolution of the state of the universe or the system, which is described formally by the Schrödinger equation, is formally described in these terms as the vector rotating in the Hilbert space. And again, this rotation can be described using any basis or any coordinate system of the quantum state. This is the case. This rotation, continuous rotation, takes place as long as there is no what is called measurement of the system. When we don't look in a sense at the system, this is how it evolves. However, when a measurement takes place, and we don't go into what a measurement is, but we just understand it intuitively at this point. When a measurement takes place, two things happen. I mean, these are two aspects of the same things that happen. When we measure a physical quantity, which is technically called in quantum mechanics an observable, when we carry out such a measurement, two things happen. First, the set of possible outcomes of this measurement is represented by the axis of the coordinate system of a certain basis. So each observable is associated with a certain basis. So until now, all the bases were just the formal representations of the vector. But once a measurement is carried out, there is a certain basis gets some intuitive preference. It represents the set of possible outcomes. And the probabilities of those different outcomes is given by some features of the vector. Okay, so first we have a set of possible outcomes. Second, the actual outcome is one of the basis elements, one of the coordinates in this coordinate system. So we have here in the terms that were introduced, we have a distinction between possible outcomes and then a selection. Now, how this selection takes place is a point we do not address here, but the whole thing of the whole issue of what happens, why is this basis chosen, and how one of the basis elements becomes the actual measurement outcome, all of this is called the measurement problem in quantum mechanics. So we have in quantum mechanics two different ways of evolution. One is the continuous Schrödinger equation, in which the vector, so to speak, rotates around the center, and a discontinuous event, a nonlinear event called the collapse of the quantum state, in which the vector collapses onto one of the axes of the coordinate systems. Okay, and different ways of understanding the measurement problem, what goes on in the measurement, give rise to the so-called interpretations of quantum mechanics, which are different ontologies that explain what's going on, why we have these two ways of evolution, how the collapse comes about. This is all we need to know so far about quantum mechanics. Example. The example is illustrated in the lower part of the third page. Consider a measurement of a quantum property called spin. Spin is a very strange property of particles, in our example of electrons. And this property is such that the electron reacts or interacts with magnetic fields, and the magnetic fields can change the trajectory of the electron because of the electron's spin. So you can think of a spin as some magnetic property it's more complex than that, but we're not going into details of this property. We'll just call it speed. That's enough for us. So the experiment in which speed was discovered, and it's still a paradigmatic case of measurement in quantum mechanics, is called the Stern-Gerlach experiment or setup. And it is the following: an electron comes out of the source, passes through a magnetic field. The magnetic field is created by an asymmetric magnet that is oriented in some direction. And so, for example, if the magnet is oriented along the z direction of space, and we have a screen after the magnet, we will observe 2 points of electrons hitting the spin, one up in the z direction and one point down in the z direction. Each electron will hit either the up position on the screen or the down position on the screen, and then we will then say that the electron had an up z spin or a down z spin, and this is the way that we explain why the electron hit the screen in that way or the other. And of course, to connect it to the formalism that we described before, the state of the electron rotates around the axis in the coordinate system, but when it hits the screen, there is a collapse in either the up z spin or the down z spin. Okay, now where am I? So yes, and we can of course carry out the same experiment where the magnet is oriented in the x direction instead of the z direction. And if we oriented it, we orient the magnet along the x direction, we will observe hits on the screen on the up x or down x directions. You can think of it as left and right, but it's usually called up x or down x. So depending on the orientation of the magnet, you will observe on the screen. We know from experience that we observe either up or down according to the orientation of the magnet. All of this is known from experience. When I'm saying that according to the orientation of the magnet, we're going to get either up or down in that direction, this is known from experience. And the question is, why do we see that? What explains the fact that we see the 2 points, the either or, either up or down in the z direction when the magnet is oriented in this way, and either or left and right where the magnet is oriented in the x direction? Why is that? What explains this experience? And we're seeking an explanation from quantum mechanics. So the theory should predict that if we arrange a magnet in this orientation, this is going to be what we're going to see. A very simple requirement from the theory, right? Now, the intuition is this. Well, the explanation is the magnet. The magnet, the fact that the magnet is oriented in the z direction explains why we are going to we're going to see hits in one of those 2 points. It doesn't explain why we see up or not down. That's a different question. But the fact that this is the set of possibilities, the set of options, is explained by the orientation of the magnet. This is the intuition. This is a classical intuition. It comes from our acquaintance with magnets and from the intuitions that come from classical physics. But we will now show that when we are going to try to explain this experience using the resources of quantum mechanics, this intuition is misleading, it is wrong, it is mistaken. Quantum mechanics does not explain this experience, okay? Digression to quantum computation, because we will show this riddle, that this lack of explanation in the context of quantum computation, because this is what we're interested here, and this will lead us to the counterpart of the indeterminacy of computation point. So, what is quantum computation? In fact, when we describe what quantum computation is, you will easily see that there is a strong analogy with the classical case. Quantum computation is the following: you prepare a system in some initial stage, very carefully prepared, of course. Then you create an environment in which this system will evolve, and you let the system evolve for some time. And at some point, some pre-designated time, you measure the state of the quantum system. And the measurement outcome is the outcome of the computation. So it's very much like classical computers. You do the same, but in the context of a different physics. And this will bring about the differences that we'll see now. Okay, so now the notion that I would like to introduce now is the notion of the computation basis. So suppose that I prepare a system in order to carry out the quantum computation. I prepare it in some quantum state, and I let it evolve somehow. So it, the physics, the Schrödinger equation just describes how the system evolves. And then comes the time for measuring the system. Now, before I measure the system, as I said, all the bases are on a par. There is no preference for any basis, only the measurement creates this preference. So when I choose how to measure the quantum state at the end, after the evolution, this measurement, the choice of the measuring device, brings about a preference for a certain basis as the set of possible outcomes. So once I choose what to measure, this chooses the set of possible outcome, namely, in other words, the set of possible outcomes of the computation. And so the basis chosen by the measuring device will also determine what we call the computation basis. The computation basis will give us the set of possible outcomes of the computation. Now, since at the beginning, before the measurement, we could write the vector in any basis whatsoever, it's convenient, if we know what we're going to measure, it's convenient to write this basis from the beginning using what we anticipate is going to be the computation basis. So if the computation basis is the up-down in the z direction, we will write the state from the beginning using the coordinates, the z coordinates. And if we plan to measure x, we'll write from the beginning using the x coordinates just because of convenience. So this is our computation basis. Okay. So we can think, for example, about the Stern-Gerlach experiment that I described before as a computation of some interesting yes/no question. So if we get z up, it will be a yes, z down will be a no, and we will orient the magnet and introduce other things in the environment that you lead the electron in the way that you want, so that the electron will collapse onto the desired outcome, and this will be the outcome of the computation. Okay, so and now let's have a look at the way that these ideas are written down in quantum mechanics. I'm not going to carry out any calculations, but it's important to see how these things are written down, because this will lead us to see how the indeterminacy of computation looks in the quantum case. So let's look at page 3 top. We have we're going to begin the quantum computation by preparing state. And as I said, since we anticipate, for example, measuring the Z spin, we will write it in these terms. And we have the expression here in bold. We have a Z up of the particles plus Z down of the particle. This is what's called in quantum mechanics a superposition. That is two options, the two options that we anticipate that we're going to measure. They are, they don't, it's not, well, they exist in a sense, in a superposition. It's not it's not an or case. It's not that either this or that exists. It's not that both exist. It's a kind of superposition. We won't go into this, but it's a kind of combination of the Z up and down, and they become either or only upon measurement. So we have here the Z up plus Z down. Normally they are written with some coefficients which determine the probabilities of the different outcomes. We omit those here for simplicity of notation. Okay, now second stage of the quantum computation, there is a Schrödinger evolution. During the Schrödinger evolution, an interesting thing happens in quantum mechanics. So we have here the next expression in bold. So initially we have the superposition of the electron in the Z up plus Z down state, coupled with or together with or at the same time with the measuring device, for example, the screen being in some ready state. It doesn't have the hits yet. It's ready to receive the hits of the electron. And as the electron evolves, a very strong connection and entanglement, we say in quantum mechanics, it comes about between the electron and the screen. And as the electron maybe almost or hits the screen, but before there is a collapse, before there is an actual outcome, the entangled electron and spin become have the state that I described here as the Z up of the electron being together with the Z up hit on the screen plus the Z down of the electron coupled with the Z down on the screen. So at the beginning, the electron and the screen states were separable. They were two independent entities or two independent states. But after they become coupled so that the screen will reflect the state of the electron, they become entangled in this way. So in the world, there is either electron up and screen up or electron down and screen down. They are entangled. And then, according to standard quantum mechanics, a collapse takes place in which only one of those two options becomes real. This will be the outcome of the measurement. Okay, this is number 3 in this list. At time t, at the designated time, we carry out a measurement. We have the outcome, end of computation.
Only.
Yes.
Just the plus here means conjunction, or what does it?
It's a superposition. It's superposition. It's a special kind of quantum mechanical thing. Okay, and similarly will be for the x direction. All right. So, but it's important for us to remember that we have these options and that so before the entanglement with the screen, we could write this if we plan to measure X spin, we would write the initial state of the electron in terms of the X coordinates, as we have here X up plus X down of the electron. And the screen will still be ready. The screen doesn't know what we plan to do, but as the system evolves, the screen becomes entangled with the electron, and this time the entanglement is expressed in the X terms. So X up electron plus right screen plus X down electron and left on the screen, and then a collapse occurs. So far, the standard quantum mechanics and the way that quantum computation is seen in these terms. All the quantum computations, the quantum algorithms that are developed in physics and computer science today are more complex versions of this simple idea. But the idea is basically the same. Normally, they have many more options, not only a yes/no question, and the probabilities are planned accordingly, etc. But the idea is this simple idea.
Because the measurements are more complex.
Yes, the whole thing is just more complicated, but it's the same idea. That's the basic idea. Okay, well, now given this very general understanding of what quantum computation is, we proceed to see the counterpart of the indeterminacy problem as it arises in quantum mechanics. And we'll see both the similarities and the dissimilarities between the classical case and the quantum case. Okay, so I will just read this and stop wherever I'm able to clarify something. So up to now, we considered two setups. One with the magnet oriented in the z direction, in which case, according to experience, and we emphasize this, the hits on the screen are up and down in the z direction, and another with the magnet oriented in the x direction, in which case, according to experience, the hits on the screen are right and left, or up and down in the x direction. But let us consider again a case where the magnet is oriented in the z direction to see why quantum mechanics does not explain nor determine these experiences. So, the state after the interaction of the electron with the magnet, but before the collapse, before hitting the screen, is standardly written in the following way, as we've already seen. Now, so we have the superposition of the electron and the ready state of the screen, and then the entanglement of the spin and the screen. Now, seeing this expression, we expect to see, right, the standard thing, the intuitive way that we think of such interactions. But now, let's do the following trick. Let us just rewrite the same expression. We're not changing the physics. We're not changing the setup. We're not rotating the magnet. We're not touching the screen. We are just rewriting the same expression using a different coordinate system. So this is just a pure formality. We wrote before in terms of the z basis because it's convenient, because we expect from experience to see hits along the z direction. But now we don't mind about, we don't care about convenience. We just want to write using a different basis. So we're going to write the same vector using a different basis, namely the x basis. And since these are coordinate systems, as usual, we can, as in a standard coordinate system, we can write the coordinate basis, one coordinate basis in terms of another coordinate basis, each coordinate using some other coordinate basis. This is what we're going to do here. So we're going to write the x vectors in terms of the the z vectors in terms of the x basis. So that's pure formalities. We're allowed to do this. This is just notation. And so this is what we do. We write each I will just show the result. I'm not writing here all the calculations. They're not difficult. If you want, we can do them later. So the z up vector basis is a combination, can be written in terms of x up plus x down. And the same with the z down it can be written as a superposition of x up and x down with different coefficients. So we just introduce these notations and we rewrite the expression. And after just moving around the elements in this equation, what we get is the expression that we have here towards the end of page 3. We get the following expression, and I emphasize that it's the same physical state as before. So before we had Z up electron and Z up screen plus Z down electron and Z down screen. The same state is now written as following: X up, because that's the new coordinate system, X up electron coupled with on the screen up and down, up Z plus down Z of the screen, strange expression, plus X down electron, and the screen will be up Z minus down Z. So the state of the screen is Z up plus Z down or Z up minus Z down. It's something unintuitive. We can't understand what it means because it's just an outcome of writing things in a non-intuitive way. But as far as quantum mechanics is concerned, as far as the theory is concerned, this is a perfectly legitimate expression. The Z up plus Z down is a quantum state of the screen. It is meaningful within the theory, although it is not something that we can understand intuitively. We don't understand what does it mean for the screen to be hit in the Z up plus Z down location. It's a non-local property. It's something unintuitive. It's not that the electron hits in two places or either or, it's something else. It's a non-local property. Now, we have here two expressions that are mathematically equivalent. And as far as the theory is concerned, they are two ways of describing the same physical state. And the question is the following: why do we, from experience, always see the hits on the screen in terms of the local quantity of the first expression, Z up and Z down, rather than in terms of the non-local funny combination that we have in the second expression? Because they are equivalent. This is a quantum mechanical counterpart of the indeterminacy of computation, because we have here two bases describing what's going on. But if we follow the Schrödinger equation in the two cases, we get different calculations, different computations of different yes/no questions. So this is in the philosophy of quantum mechanics, this is called the basis problem. The basis problem is this: we can write the same state in different bases. Why do we see only one basis rather than all the others? And since these two ways of writing the expressions are formal, straightforward outcomes of what I told you about quantum mechanics itself has no resources to choose between these two options. You might say that one is intuitive and the other isn't, but from the point of view of the theory of quantum mechanics, they are on a par. Quantum mechanics is unintuitive, throughout, everywhere you look. So being unintuitive is not a good argument in this case. So quantum mechanics cannot explain why we see one computation rather than the other. And the two, in a sense, take place together, but not in the classical sense of taking place together. And we'll see this in a moment. So that's the indeterminacy of quantum computation. So the last paragraph of page 3 reads: what in quantum mechanics explains our experience in which we invariably see an electron hitting the screen in either the state up or the state down, concluding that the electron spin is either Z up or Z down, why don't we see the other counterintuitive options of up plus down or up minus down? This is the basis problem and the indeterminacy problem. So these are the basis problem and the indeterminacy of quantum computations are the two ways of describing the same fundamental problem in quantum mechanics. There are analogies with the classical case and disanalogies, and we turn now to briefly tell you about those. So the analogy is that obviously the same system undergoes the same microdynamics, but you can see it as carrying out different computations. But the disanalogies and the differences are huge. First of all, it's impossible to prefer or focus on one option rather than the other in quantum mechanics. In the classical case, you could say that the environment chooses something, or there are semantic properties of one computations and not others, or physical properties of one computation and not others, and in this way choose or prefer a computation and solve the indeterminacy problem. In quantum mechanics, that's impossible because of theorems. In quantum mechanics, if you prefer one basis in that sense and say that this computation took place rather than the other, you run into contradictions. So that is not allowed by the formalism. It's impossible. There are theorems, Kochen-Specker and Corley theorems that prevent this even conceptually. So that's not an option. It's also impossible to say that all computations are carried out simultaneously, as Nir would like to do in the classical case. That's impossible in quantum mechanics as well, because of other theorems in quantum mechanics. That's impossible to say. If you say that, you also run into formal problems. So these two computations, you can't say that one is preferred. You can't say that all of them run in parallel. So there is a very deep indeterminacy problem in quantum computation, which is much stronger. The situation is much more severe in this case than in classical computations. So if there is hope that quantum computation will give us some solution to the classical problem, forget it. It's worse. These things are only worse. Great. So that's a situation with a standard quantum mechanics in which the theory is, as I described in the beginning, a vector in Hilbert rotating in Hilbert space according to the Schrödinger equation. There are, however, non-standard theories of quantum mechanics that try to explain the collapse. The theories that try to explain the collapse add something to the theory. They're not just interpretations. They're called interpretations, but they're not merely interpretations. They change the dynamics or they add things to the ontology. They are different theories. Now, if we have these, if we adopt any of those so-called interpretations, different theories, different ontologies, then these ontologies give preference to some basis. And if they do, and they also explain why the system collapses to one vector among these options. If we change the theory in this way and give a preference in the theory to one basis, then the indeterminacy is solved. And there is, in a sense, there is no problem to begin with. There is only one computation. Notice finally that this is in the non-standard theories. And notice that in that case, the microscopic trajectory of the quantum system is the computation, and there is no option even to see it as computing different things. So the theory tells you that either there is a one well-defined quantum computation, or there is a hysterical indeterminacy that you cannot solve in the theory. And in both cases, it's not up to you. It's not as if you can introduce probes and select something. It doesn't work in this way. I think I'll stop here. Maybe Meir wants to add
Maybe
something.
just one point before the discussion. I just want to stress something that already said, that, and this is a controversial point. I'm trying to explain why, and it is this. There are, in the context of quantum mechanics, different theories or different interpretations. One of them is called the many worlds interpretation, for example, in the literature. And it is the challenge there is not to introduce any changes in the theory, so they only work for the Schrödinger equation, that's all. On the other hand, as already said, if you're only working with the Schrödinger equation, there is no preference for any basis. And the challenge that they have is because our experience does prefer basis, because as we said, when we look at the outcome of the measurement, we see one outcome out of a certain set of possibilities rather than another set. So our experience does prefer basis, and the challenge for them, for the many world theorists, is to somehow solve that problem without changing it, without touching the Schrödinger equation. And we think that it is possible to do that. They think that it is possible, so there is a controversy which we should point out. As if we are right, as we said, then without changing the Schrödinger equation, we are facing the indeterminacy of computation, and there is no way to solve that problem. The only way to solve it is to change the physics, the quantum physics, and then the nice result is that there will be no multiplicity at all, or no indeterminacy at all. By contrast to the classical case, whereas in the classical case, one can see the indeterminacy as being created because there are side to side different macro variables of the system which are there, like as I said before, temperature or pressure or volume or voltage, they all exist simultaneously. In quantum mechanics, it is impossible. So the way to solve the problem in the case of quantum mechanics, if you don't change the physics, we think is impossible. That's
That's it.
You both use the problem word quite a lot. On the hand, you've got the classical indeterminacy problem, and then the problem's more severe with the quantum case.
Right.
I've never been persuaded that there is actually a problem.
Yeah.
It's more
Yeah.
that computational indeterminacy just is so. It's
Yeah.
like it's a phenomenon.
Oh,
And the question is kind of, now we've noticed the phenomenon, what can we do with it, if anything? Can we make use of it? So that's my question. Can you envisage any uses for the indeterminacy of quantum computation? What can it buy us?
well,
Can I
let's,
answer?
yeah.
I think that the problem is, the reason we say problem is because we work in a certain context, and the context is the computational theory of the mind. So if the brain is the computer, and you think that the mind is some sort of a computation, then the indeterminacy or, I mean, if you want to call the problem, a problem of indeterminacy, then it means that the physics of the brain doesn't determine the computation, which is the mark. We usually call it not the indeterminacy, but the multiplicity or the multiple computation situation. But and then you will have something like a minima. So you have a brain which implements at the same time too many lines. And then there will be the question, what selects the mind, which is what selects the computation, which is our mind. And this is what we call it.
Well, maybe nothing, maybe some kind of super scientist looking down on your brain, but by two different ways of kind of interpreting it. So it's like you're having these thoughts or these completely different
So you mean that
why does it matter?
Well, we think that it is a problem because, I mean, I think that, I mean, one wouldn't want to say that, my mental state now, which is a computation, according to that theory, is determined by some other being which looks at you or measures you or something like that. That would be a good solution for the question what the laptop is computing. Okay. But not for the computation of theory.
I personally, I'd be fine with saying there's no practical matter as to what your thoughts are. But what about the application? Is there anything useful you envisage being done with quantum determinism?
We do that, that's maybe a bit technical, but we have some ideas to overcome decoherence problems in quantum computation and so on, using these ideas, as well as identifying the computation. Well, that depends if your standard, that depends on your theory. According to some theories, it will give you a hint on how to plan the computation and to carry it in a clever way, given decoherence effects. But that's too technical for us now. But it's not about the mind as a computer. It's about quantum laptops. So we don't know. But
yeah, I just wanted to ask about. I don't see how in this analogies section 1.1 and 1.2.
yes.
I mean, don't they contradict each other? I mean, you say it's impossible to postulate that all computations coexist because of the incompatibility of the basis problem.
Yes.
If it's impossible, then you have to say that one exists or none exists. But then in 1.1, you say that it's impossible to prefer.
Yes.
Computation basis, so it seems that there is a contradiction, not really.
Yeah, it's a result of these ideas of superposition and entanglement in quantum mechanics. So there is a theorem according to which if you say that a certain basis, the properties associated with a certain basis exist before measurement, there are theorems that show that you run into a contradiction. So, and there is no, so this is why you can't prefer. At the same time, there are theorems that Itamar used to emphasize, according to which there's no joint probability basis. So that you can say that before the measurement, you could, for example, you could suppose that you have half and half probability for measure in the z direction and half in the x direction. So you can't say that you have a quarter, 25% chance of having x up or x down. You can't have these together, they're exclusive. So this is why these two in the quantum context, I understand why they seem counterintuitive, but it's not, it's the weirdness of the theory. I can only show you the theories.
I guess a clarification question. And maybe Explain how it relates or doesn't relate from classical and municipal. In regards to the implementation, when you talk about the classical problem, so that the physical, semi-physical process implements multiple computations. And it simply we didn't really use that kind of phrasing here. It was more of kind of to describe what is actually going on as different computations. We didn't really talk about it as implementing, and maybe and there's a sense in which kind of we're looking what is actually going on, what they're actually experiencing, and we could determine how we should think that in the sense of implementing that there is one option that has been implemented, the one that is consistent with what they're experiencing.
Well, if we understand experiencing as the measurement outcome that somehow tells us what went on, right? We probe the system. So we probe the system, whether it's a quantum laptop. So by some probe, by the measuring device, we will select one computation, or or maybe something that gives rise to our experience is doing this job. So in both cases, what you have is the quantum system and something that measures it and thus prefers a certain basis. But what we've shown is that because of this entanglement between the system and the measuring device, the measuring device is not external. It's not something that in quantum mechanics, a measurement is not looking at the system. A measuring device becomes coupled with the system very strongly. And so the measuring device enters a superposition that was before the superposition of the particle. So and if you want to bring about a collapse, you will need another measuring device, but then it will be coupled again. So nothing does the job of selecting the basis for you. It only becomes more and more coupled. So nothing will make it the case that you experience one of them and not the other. Quantum mechanics can't do this work for you unless you add something to the theory. Yes, and then it selects, but then it's not up to you. The theory, then the problem doesn't arise. There is no multiple computations, and not even in the sense of the singles that you introduce. There is no slutting and not roaming and nothing like that.
What determines the measurement?
That's the measurement problem, and in standard quantum mechanics, that's an open question. Nothing. There is no such thing because there is no collapse. To explain the collapse, you need to bring it in something from outside of quantum mechanics, and this theory, and then the theory tells you what selects it. According to some theories, the position basis does it. According to other theories, the size of the system does it. It depends on the interpretation, but the theory selects the basis for you, and that will be the basis.
The sound that you or the quantum resolve the indeterminacy.
I don't know. I can only tell you about different interpretations, but maybe Meir has a.
No, I just want to add some other points, which I think is also very interesting in the quantum case, and which is very different from the classical case. In the classical case, we think that the way to think about the indeterminacy problem or the multiplicity problem, and depending on how you want to call it, is to think about the computing system as having the same microphysical description, same microphysical process, but there are different macroscopic properties which evolve over time and which are parasitic on that microscopic description, but they evolve differently. This is also what gives rise to the thermodynamics and probabilities in classical physics, which is deterministic. Now, in quantum mechanics, it turns out that you can't think about a system as having both a microscopic description and a macroscopic description, which is parasitic. Namely, if, for example, you take, you have a box and you have a particle in the box, and you want to know whether the particle is in the right side or the left half of the box, and you carry out a measurement, that's a sort of a macroscopic measurement, but in quantum mechanics, it's just microscopic. Because once you carry out that measurement, the particle will be smeared all over either the left side or the right side. It will not have a more fine-grained position. So there is no way of splitting between the microphysical description and the macroscopic description. And this is why, if there will be a solution, I mean, if the theory is able to solve add a basis to the quantum mechanics by changing the theory, then it will also solve the indeterminacy of computation problem. There's no way to describe different macroscopic properties of the system, which will carry out for different computations depending on what the observer depending on the way the observer interacts with that system. Whereas in the classical case, this is the way we can do the way to understand the problem. So there's a big difference between the two of those.
So when you say solve the problem, you mean solve the multiple minds?
Yes.
Yeah.
Yeah.
So if the mind, if you think about the mind as a quantum system, and you have a solution to the indeterminacy problem, then you can stick to the computational theory of the mind. I mean, at least insofar as the indeterminacy of computation problem is concerned, you don't have a problem. But so it's advantages and disadvantages to go in the quantum theory.
So yeah, quantum mechanics is often associated in the literature with talking about the mind. There is the observer, and so there is something that we choose. We can choose, the observer can choose the properties, etc. But we think that quantum mechanics is in fact not a good theory for explaining the mind. That if classical theory were true, it would be a better theory for explaining the mind, because in quantum mechanics, either you introduce, in most interpretations, either you introduce the mind to begin with in order to explain the collapse, or you can't choose between these different bases if you don't introduce the mind. So it's not a good theory for that.
There isn't just one. So, so the question is whether your maybe result is too strong. Maybe the result is that quantum computation is impossible at all, no?
Well,
Because, yeah.
Neil?
Well, I think that I mean, if we could, depends what you mean by quantum computations. Let's put aside, let's put aside the problem, basically the most difficult problem of isolating the computer, the quantum computer.
No, because there is an indeterminacy. You
Yeah,
can't.
so let's
You
put-
can't.
Yeah.
You
Yeah.
can't prefer one, and
That's
so
That's right.
yeah.
That's why quantum theory without change, I mean, according to experience, we should be able, if we set aside the technical problems, we should be able to implement quantum computation according to experience. But according to the pure theory,
Mm.
namely standard quantum mechanics, without aiding ourselves with the collapse postulate, which is completely mysterious in standard quantum mechanics. So if you disregard it as well, yes, there's no way to talk about physics. So in the first place, physics is not you know, the physical theory is in a very big problem. So, you know,
So
this is the
that,
first problem. So the second problem is that you won't be able to talk also about quantum computers.
yeah, that's correct. Yeah, we know that, I mean, people are building quantum computers, right? These things are working, you know, small ones, but they're working. So, but the problem is to explain why and how they're working. And to do so using only the resources of quantum mechanics. This is not available to us. So, you know, so part we can formulate using quantum mechanics, part of what's being built, and we know how it's going to operate from experience. But then there is a theoretical huge gap. Okay, so.
So one last question, if I may, as an organizer, co-organizer. So just big picture. So quantum computation leads to indeterminacy of computation unsolvable. Perhaps quantum theory in general is false.
Yeah.
Let's put that aside. But assuming it's not, then computational theory of mind cannot be quantum, as you just said, right?
In a sense, yes.
Okay. Option two, classical computation.
Right.
If the indeterminacy of computation can somehow be resolved in the classical sense, then
Yes.
you're still partly content that computational theory of mind stands a chance.
If you give up on you have to give up on the computational theory of mind.
No, but
That's not the dilemma I suggested. I
Yes.
said,
I know, but
you have,
Yeah.
okay, so why do you have to give up? it?
because if the mind, so we're now talking about the classical field. Sure. The brain is a classical system. Sure. I mean, if you're saying as a computationalist that the mind is a computation. Okay. Now, we know from the problem that the physics of the brain cannot single out the computation, which is the mind. This is what the problem means.
Why do we talk about the mind and not just cognitive processes?
Cognitive process.
Cognitive
Yeah,
process.
that's.
So if you have a solution to that problem, which is based on physics, on the physics of the brain, fine. But we think that there isn't.
We think that there is, according to physics, there is a property of the brain, which is identity theory, the cognitive process or whatever that is. And now, if you know, suppose that we know this property, that physical property of the brain, then the computation associated with this property will take place. Fine. But then the explanation of why this is the mind will not need the computation here. It's just a matter of convenience of description. That's all. Yeah, it's just a convenient way of describing what's going on, but it's not the deep explanation. The deep explanation will be the physics of that property. That's only possible.
With that in mind, I guess we can think about it.